okay, and develop our example a little bit further so we can get a little bit closer to the way that we were playing cards previously. So remember that we have a dealer who's got 5 cards, okay, and the dealer deals out 3 cards, okay. Now the issue with the factorial term that we dealt with last dealt with one aspect, that we would have liked it if it's just we got ace, king and queen in any order and it didn't matter how it occurred, that just meant that we won. Okay, so we dealt with that through the factorial part. The other thing that we need to deal with is the fact, to cope with, or to is the fact that the dealer, okay, is currently, or has been for the last 2 examples, taking a card and replacing it back in the deck. And we want to be in the situation where the dealer lays the 3 cards down in order without putting anything back in the deck again. Okay, so let's deal with that case. So the rule we're going to consider, okay, is we're going to consider the dealer deals the 3 cards in a sequence without replacing them. Okay, so just puts out the first card, then the second card, and then the third card, and he doesn't, once a card is down on the table, he's not going to put it back in the deck again. Okay, and we're going to say that you win if you get ace, king and queen in that order. Okay, so the first card needs to be an ace, the second card needs to be a king, the third card needs to be a queen. Okay, all right. Okay, so again we've got a dealer. The dealer's got a pool of cards: ace, king, queen, 4 and 2. Okay, now we've got our positions that we're going to put our 3 cards on the table. Okay, so you can imagine that we've got card 1, card 2, card 3. Okay, so what the dealer's going to do is going to take a card out, put it in the deck, put it in the position where card 1 should be. Takes another card out and puts it in the position in front of us where card 2 should be. Takes out the third that's remaining and puts it in the deck in the position where card 3 is listed here. Okay, so we now need to think again, all right, what is the sample space, what is the size of the sample space for this problem? Okay, so what are the number of things that can happen, okay, in terms of putting the cards here from this deck? Okay, so the one way to think about this is as follows. Let's think about the number of things that can happen for this first card. Okay, and then given what happened here, what are the number of things that are left over for the second card? And then given what happened with these 2, what can happen to the third card? So again, we're just going to go into this sort of tree example. So we want to find the size of our sample space in this setting. Okay, so it's a slightly different setting because we don't replace, well, deals with 3 cards in sequence. I'm just cursing myself. We should say without replacement. Sorry about that. So you deal the card, you don't put it back in the deck. Okay, so excuse my writing, not what I'm saying. Okay, right. So let's start at time 0. Okay, there are now 5 things that can occur to that first card here. All right, we could get an ace, a king, a queen, a 4, or a 2. Okay? But once you've been given that ace, well, it's no longer in the deck anymore. So if we look at what happens at the next time period, well, there's really only 4 things that can happen now. Just do like before. You can get a king, a queen, a 4, or a 2. Okay? And then, and equally, we would get 4 branches out of here, and 4 branches out of here, 4 branches out of here, and 4 branches out of here. Okay? Then, okay, for the third card here, alright, we've got an ace out of the deck, a king out of the deck, so there's only 3 cards left, a queen, a 4, and a 2. Okay? So we could get a queen, a 4, or a 2. And then similarly for here, there's 3 things that could happen, 3 things that could happen, 3 things that could happen. Okay? So, if we drew out this tree, which I don't have time to draw everything out on, we notice that there are 5 initial branches, and then from each of those you get an additional 4 branches, and then from each of those you get an additional 3 branches. Okay? So if you look at the total number of items or ways from getting from this root to the leaves of this tree, okay, there's going to be 5 times 4 times 3, okay, which happens to be equal to 60. Okay, so in this case, omega is equal to 5 times 4 times 3, which is equal to 60. Okay. And notice, out of all of these possibilities, only one of them is the winning possibility, this one, where you get ace, king, and queen. Okay? So the probability that you win, in this case, is 1 divided by 60. Okay? Now notice, what we looked at here is something a little bit like a permutation, okay? But it stops short, a bit like a factorial, but it stops short at 3. Okay? So that leads us to a new definition, and that's for permutation. Okay, so definition. Permutation. Okay. So notice what we did is we took out 3 elements, okay, into a list in order from a list of 5. Okay, so that's essentially what a permutation is. It's the number of ways of taking k items from a set of size n. Okay, so in this case we took 3 items out of a set of size 5. Okay, and I'll add one caveat that here the order mattered. Remember that there is a difference between taking ace, king, queen compared to taking ace, queen, king. Okay, so we don't treat those as the same thing. Okay, so the number of ways of taking k items from a set of size n where the order matters is written as follows: P, N, K, okay, where, like before, we've got n times n minus 1 times, okay, so we've got 3 terms here, but in this specific case we'll get k terms, so we go all the way down to n minus k, and notice we're going to add a plus 1 on here. Why is that? Because we sort of started from 0, so we've got to go down to the k minus 1 plus 1th term. Okay. Another slightly neater way of writing this would be this to be n factorial divided by n minus k factorial. Okay? So we've got the first, so we product up the n terms and leave it so there's only k left. Alright? Okay? This is called a permutation. Okay? Alright, so we've almost got there. We've sort of dealt with two concepts separately. So notice here, by considering permutations, we've dealt with we now have the issue of the dealer putting the cards back in the deck sorted. Okay, so now the dealer just deals out 1, 2, 3 cards as you'd normally expect. And here we separately dealt with the issue that we didn't want to care about the order that the cards came out in. Okay, so ace, king, queen was the same as queen, ace, king. Okay. So now we just need to put these two ideas together and we end up with what we call combinations. Okay. Okay. So now the rule's going to be, okay, so the dealer deals the 3 cards out without replacement. Okay, so just never puts any of the cards that he gives out back in the deck. Okay, and you win if you get ace, king, queen, okay, in any order. So this is probably the formulation you're expecting from the question. It's also kind of the same way like the National Lottery works. Okay, it's not 5 cards and 3 that are dealt out. It's more like sort of 59 cards and 6 that are dealt out. Okay, but the format's essentially the same. Okay, so I'm going to look at this the way we've been looking previously to start with, and that will help us do the calculations for this. Okay, so one way to look at it is to think that we've got our state space exactly as before. Okay, so in that case we have an ace, a king, a queen, a 4 and a 2 in the deck of the dealer. Okay, and then we have 3 cards. Card 1, card 2, card 3. Okay, so here's the spaces where the dealer puts your 3 cards. Okay, and in this case we counted up the number of elements in the sample space. Okay, it was I think 60. Yeah. Okay, so there are 60 ways of putting 3 cards in these 3 positions. Okay, sorry, there's 60 ways of putting these 5 cards into these 3 positions. Okay, and now one such outcome would be queen, ace and king. Okay, and that would be a winning hand. But in addition to that, there are other winning hands. For example, ace, king, queen would also be a winning hand. Okay, so the number of ways of winning here, okay, is exactly as we calculated before when we were looking at the factorials. There are, so the number of winning hands So the number of hands here that win is equal to 6. Okay? So the omega equals 60 comes from here. Okay? And the number of ways of winning is 6 comes from here. Right? So convince yourself that those two calculations are exactly the same as we previously did them in this case. Okay? So the probability that you win is equal to 6 divided by 60, which equals 1 in 10. Okay? Now write that out a little bit more explicitly, because remember that the way we calculated 60, okay, was 5 times 4 times 3, okay, and that's right, which was equal to 5 factorial divided by 2 factorial, okay, and the way that we calculated this 6, okay, was 3 times 2 times 1, which is equal to 3 factorial, okay. So really the calculation that we did here was 3 factorial divided by this number, which is 2 factorial divided by 5 factorial. Okay? Now, so if we're going to come up with a general formula of this, it's going to look something like this. Okay? But let's think about another way to conceptualize this. So notice I've treated this. Remember that we said that you could have more than one way of representing your sample space. Okay? This is a way that we represent our sample space by triplets of cards. Okay? So in this case, omega is sets of cards, where this is the first card, this is the second card, and this is the third card. And the cards themselves, each card, okay, must belong to the set ace, king, queen, 4, 2, and obviously no two pair of these cards are equal. Okay, let's not worry too much about the exact way to write out this set. All right. However, within this, we have to consider more than one element. Okay? Another way to conceptualize thinking about this state space and writing out a slightly different state space, okay, is as follows. So another way is again to think of the dealer having an ace, a king, a queen, a 4 and a 2, okay, and then rather than having 3 places for the cards, you've got sort of your hand. Okay, your hand is just means you can hold 3 cards, and it doesn't matter which order you decided to hold them in. Okay, and then so what the dealer's going to do is put 3 cards into your hand, and you're going to hold them, and it doesn't matter which order you put them in. Okay. Similarly, the remaining 2 cards are going to remain in the dealer's hand, and he doesn't really particularly care which order they're in either. Okay. So this is the hand dealt, and this is the dealer's hand. Okay, the 2 cards left in the hand of the dealer at the end. Okay. We could think of this as a new state space, or as a new sample space. Okay, so in this new sample space, we're considering sets of cards. Okay, card 1, card 2, card 3. But now the order of this set doesn't matter. So the set card 1, the set ace, king, queen is equal to the set ace, queen, king, whereas the coordinates ace, king, queen, okay, is not equal to ace, queen, king, right? Okay. So such that card 1, card 2, card 3 belong to the set ace, king, queen, 4, 2, and no two of those cards are equal. Okay, so I could write that here, but let's not worry about that. Okay. So then we know under this probability space, this sample space, the probability you win is equal to 1 over omega tilde. Okay. But then I've also up here done the calculation for what the probability of winning is. So I've actually counted the number of ways of dealing hands at mere hand with 3 cards. Okay. So notice from this being exactly the same, a slightly different way of representing the same experiment. Okay. We can see that the number of items and the number of outcomes in this sample space is given by 5 factorial divided by 3 factorial and 2 factorial. Okay? So in other words, we found out by writing this out a slightly different way that the number of ways of choosing three items, should we say, from a list of 5, okay, is 10. Okay. So another way to think about this, just one more, is that I could think of these being the 5 cards in the hand of the dealer, and I put a black spot, okay, over the cards that the dealer gives to me, and a white spot over the cards that are left at the end. Effectively, what this counting is doing, the number of elements in this set, is the number of ways that I can write these black spots on top of these cards. Okay, so the number of ways I can combine these white and black spots so that there are 5. Well, there are 5 in total, and 3 are black and 2 are white, gives me the total number of ways of dividing up this deck into a group of 3 and a group of 2. Okay. Another thing to notice is that here this was equal to the permutation of 5 and 3. Okay. And then we just divided it by 3 factorial, okay, to get this term here. So notice also that this term is equal to the permutation of 5 and 3 divided by 3 factorial. Okay? Alright, so what's the long and the short of all of this is that we're essentially coming up with a kind of formula for the number of ways of choosing a number of items from a larger list. Okay? And that's what combination does. Okay? So I'll just explain that here. So definition, a combination okay, the number of ways of choosing a set of k elements from a larger set of n elements, okay, is given by the following what's called binomial coefficients. I'll discuss a bit why it's called that, and probably in a different video. But essentially, the binomial coefficients are written like this: C, N, K, or like this. Okay, so kind of a big brackets with an N and a K, and no divides here. Sometimes people write kind of division sign, that shouldn't be there. Okay, and this is, which is equal to, just like we had above, Pn K divided by K factorial, which by a formula from before was equal to N factorial divided by N minus K factorial divided by K factorial. Okay? Another way of writing this out is we've got N times N minus 1, and we do that for K terms, so N minus K plus 1, and then we divide it by exactly the same thing, but we start with K, and we take the K terms going down from K. Right? And when we talk about these expressions, we say N choose K. Right? So essentially, if I have a list of N items, let's suppose I've got a list of just, let's say, numbers up to N, and I want to put, let's say I want to mark them with K marks on top. I want to consider the total number of ways of placing those K marks on top of that set. The number of ways of doing that is this. Right? And in particular, in our case, the number of ways of winning, the probability of us winning this game of cards was given by 1 over C 5 choose 3. Okay? Just as if I looked at the national lottery, the number of ways of winning the chance of you winning the national lottery is, I think it's 59 balls, okay, and the 6 that you're required to get to win it. Okay? So in the case of the national lottery, the probability of you winning the national lottery is 1 over 59 choose 6, I believe. Okay. All right. So now we've kind of got all the main tools that you need to do kind of some fairly complicated counting arguments, which are quite useful in these kind of card game situations, lottery type situations. Okay. They also occur in other settings, and we'll discuss that a little bit more probably at another point.